Hey, good morning, good evening, good afternoon, good night. I'll just say good day. Welcome back to Calculus, Lesson 9 in Unit 3. Today we're going to be using the idea of implicit differentiation to determine the derivative of inverse functions, more specifically inverse trig functions. Okay, so you're going to see why we needed implicit differentiation today. Okay, so with that said, our goal is to basically determine the derivatives of things like arc sine, arc cosine, arc tangent. Now, in that, I don't necessarily want to say that we need to commit these derivatives to memory. It's important to know them, but it's more important to know where they come from, how they are derived, okay? Because if you can derive them, if you can create them yourself, you're going to have a much better understanding of the calculus behind it rather than just memorizing it. But before we do that, let's take a quick look back at what an inverse function is. So remember, the idea of an inverse function is that when you take a table, for example, an xy table, the inverse of that would flip the x's and the y's. And then that's the numeric approach, the tabular approach, so that if you had something that looked like this, xy, 1, 2, 3, and this is 5, 7, and 9, then the inverse function of that would be that the x and the y's flip, so it would be 5, 7, 9, 1, 2, 3. So that's the numeric approach of an inverse function. Okay. And then the analytical approach is this idea here. So when you're given an equation like y equals 1/4 x squared minus 3, in order to find the inverse function, or the inverse relationship, you swap out the x's and the y's. So this will say x equals 1/4 y squared minus 3. And then you isolate y. So we'd add 3 to both sides. We've got x plus 3 equals 1/4 y squared. We're going to multiply by 4. So I'm just going to go ahead and distribute that. We get 4x plus 12 equals y squared. And then when we square root, we get y equals plus or minus the square root of 4x plus 12. So this is a parabola. This is a parabola that shifted down 3, something along this line, and the inverse of it is not a function. The inverse of it, we would go back 3, and then we would have a parabola here. Now, we are concerned with the idea of functions, so we would have to be able to identify whether we're talking about the top half of this parabola or the bottom half of this parabola, depending on whether this is positive or negative. Well, how do we know that? We'd have to be given some sort of initial condition. We'd have to be given a point that we can check to see if that point lives within the range of this function, whether it's above or below. So with that said, I'm not too concerned about that right now. We'll get more into that in the future, but just remembering what an inverse function is. And so we end up with, again, plus or minus rad 4x plus 12. Another example is if f and g are inverse functions, what is f of g of x, right? So remember, f of g of x can be rewritten as f of g of x, right? So what is f of g of x if f and g are inverse functions, are inverses? Well, you should already know that the answer is x, right? The inverse function, the composition of inverse functions is x. Well, why is that? Because we would have to write a statement from here, and this is going to be important. F and g are inverses. In other words, the inverse of f is equal to g of x, right? Or we could also say the inverse of g is equal to f of x. That's what this statement is saying. F and g are inverses, okay? Now from here, we want to figure out what f of g of x is. Well, in order to solve for this, we need to first figure out what f of x is so we can evaluate that. Well, how do I figure out what f of x is? In a sense, you would take the f of both sides. And so we end up with the f and the inverse of f canceling out, and you're left with f of g of x equals f of g of x equals x. Those cancel out. If you were to do that here, you would take the g of both sides, and so we would end up with g of f of x is equal to x. Because again, these cancel out. And so you can see, what is the composition of inverse functions? Well, it is equal to x. We can check that is true in our previous example here. Okay. In our previous example, we had our two functions. We had y equals 1/4 x squared minus 3. And then we had the inverse of that. The inverse was y equals radical 4x. Is that right? 4x plus 12, right? And we could do the plus or the minus. It shouldn't matter. Plus or minus here. Now I'm going to name this. I'm going to call this f of x. And therefore, this would be the inverse of f of x. So if I want to know, if I want to check to see if these are inverses, maybe I'll call this g because g is the inverse of f. I need to figure out what f of g of x is, or g of f of x. It doesn't matter. Here we would get 1/4 of x squared. Well, all of this plus or minus radical 4x plus 12 all squared minus 3. Then we go to simplify this. Well, when I square this, the positive squared is a positive, or the negative squared is a positive, so you get the same thing here. The radicals reduce, and so you're left with 4x plus 12, and then minus 3. We'll distribute here. We get x plus 3 minus 3, which is just x. So you can see that the composition of inverse functions is x, and that's a way to check to see if they are inverses as well. Okay. Now, that's just a quick review of inverse functions. Hopefully, you're pretty comfortable with that. I know that if you were in my Math 2 Enhanced class, you've seen that before. You should have seen that in Math 3, though, at the very least. Okay. Now, the derivative of inverse trig functions is where we're going with this. You go, well, how is that related to the derivative of inverse trig functions? Well, they're directly related, and you'll see why in a second. The example I'm going to give you is, let's say we have y equals the arcsine of u, and I want to know what dy du is. That's the question. Okay. So what am I saying? I'm saying we're treating u as the variable, y as the function. We're taking the derivative of y in respect to u. Now, keep in mind that this -1 doesn't mean raised to the -1 power. It means the inverse of. Okay, so it's not raised to the -1 power. Do you know the derivative of the inverse of sine? No, you don't. We don't, right? And to be honest with you, I don't have this directly memorized either. I derived this, okay? I derived the derivative. So how could I get rid of that inverse function so that I can solve for this? Well, if you think back to geometry, basic trigonometry, what is the opposite operation of the arcsine? Well, that would be taking the sine of both sides. So I'm going to actually move this over here, and I'm just going to say y equals the arcsine of u. Well, how do I get rid of that? I take the sine of u. And if I take the sine of that side, I've got to take the sine of the other side. And so we're left with the sine of y equals u, because these will cancel each other out. Now from here, you should be able to say, well, I can take the derivative now, because I know the derivative of a sine function. Well, what's the derivative of sine of something? It is the cosine of that something. But then don't forget, you have to take, apply the chain rule. So what's the derivative of y? The derivative of y is y prime. So we're using the chain rule here because y is a function. What's the derivative of u? The derivative of u is 1 because u is treated as the variable. And then to isolate y prime, we're going to divide on both sides. We get y prime equals 1 over cosine of y. And there is the derivative of an inverse sine function, okay? 1 over cosine of y. Now, we don't leave it in this form because we want the derivative of y in respect to u. And right now, it's written in respect to y. So what we need to do is replace y with something that's equivalent to it. Now, we might say, well, y equals the arcsine of u. That was originally given. So I could just say y prime equals 1 over cosine of y, of arcsine of u. And this would be true, but this is disgusting. So we don't want to write it like that. we're actually going to go way back to geometry, and this is going to be a very important thing moving forward. Thinking about basic trig relationships, okay? If I have a right triangle, and I'm thinking through this line right here, this line is kind of our giveaway. We don't want to deal with the inverse, we want to deal with that function right there. What is this saying? This is saying sine of y equals u. That's telling me that y is my angle, because I'm taking the sine of an angle. Sine of theta is equal to u. Well, what is sine? Remember, sine of theta is equal to the opposite over the hypotenuse. So this ratio, this u, represents a ratio of the opposite over the hypotenuse. So if I labeled this as my y angle, this is my opposite, this is my adjacent, we would say, adjacent and hypotenuse. Since it's opposite over hypotenuse, we would say it's u over 1. And so we have our hypotenuse of 1. Okay? Now, we're going to do some more work because our goal is to figure out what the cosine of y is. Remember, cosine of an angle is equal to the adjacent over the hypotenuse. Okay? So we already know the hypotenuse is 1. We need to figure out what the adjacent side is so we can plug that in. Okay? So how do we do that? Well, we do the Pythagorean Theorem. I'll put a little happy face here to represent that variable. We would say happy face squared plus u squared equals 1 squared. And then we isolate happy face. So we end up with happy face squared equals 1 minus u squared, because I squared the 1. And then when we square root that, we get the happy face equals radical 1 minus u squared. And we don't do the negative version of that because we're talking about a length here. So we just say radical 1 minus u squared. This side is radical 1 minus u squared. And so we can now replace cosine of y with something of value. Y prime equals 1 over, what's the cosine of y? The cosine of y is the adjacent over the hypotenuse. So it would be radical 1 minus u squared over 1, and then that just simplifies to radical 1 minus u squared. And there we have the derivative of the inverse of sine. Okay? I know that seemed like a lot of work. Again, I don't want to fall into the trap of just committing something to memory. I want to be able to develop it. And if you can develop it, you're going to understand the whole idea of inverse functions more and more as we go along. So just a quick recap. If I have the arc sine, y equals the arc sine of u, then if I take the sine of both sides, I get sine of y equals u. And then we can look at our triangle where y is my angle and u is my opposite, 1's my hypotenuse, because sine of y is equal to u, which is u over 1. We could do the Pythagorean theorem on it. We'll get there in a second. But when I go to take this derivative, I have to use the chain rule. I have to use implicit differentiation because y is the function. So we get cosine of y times y prime. And then the derivative of u, because u is a variable, is just 1. We isolate y prime. And then we have to replace cosine of y with something of value. So that's when we do our Pythagorean theorem here, and we get radical 1 minus u squared. And therefore the cosine of y is that over that, which is just going to end up producing 1 over radical 1 minus u squared. So there is that one. Let's go ahead and take a look at the next one. See if you guys can do this on your own. Push pause, do as much as you can, and then come back and compare what you did to what I did, and make sure you're right, and make sure I'm right. For this one, it's saying y equals the arc cosine of x squared. And we are looking for y prime. In other words, if we're looking for y prime, the other way of saying that is dy dx. That's implying that x is the variable and y is the function. So let's go ahead and figure this guy out. Well, the first thing we want to do is take the cosine of both sides to get rid of that inverse function. We end up with cosine of y equals x squared. Then we take the derivative. So we end up with, well, cosine of y, the derivative of that is negative sine of y times y prime, because we're dealing with a function there. The derivative of x squared is 2x. And then isolating y prime, we end up with 2x over negative sine of y, or I'm just going to do this. I'm going to put negative 2x over sine of y. We want this to be all in terms of x, so we've got to figure out something that can replace the y. And we do that by doing our triangle. Looking at this line here, okay, I'm going to put a little arrow here. We're going to take this and plug it into that. The cosine of y, that means y is the angle, x squared is my adjacent, and 1 is my hypotenuse. From here, we're going to do our Pythagorean theorem. So we end up with x squared plus x squared squared plus happy face squared equals 1 squared, right? It's the leg squared plus leg squared equals hypotenuse squared. And then simplifying that, you end up with x to the fourth plus happy face squared equals 1. So happy face squared equals 1 minus x to the fourth. Square root it. So you end up with radical 1 minus x to the fourth. And we're going to keep it positive because we're talking about length again. And so we got this side to be radical 1 minus x to the fourth. And then we can figure out what sine is. We got y prime equals negative 2x over the sine of y. Well, sine of y is opposite over hypotenuse. So that would just be radical 1 minus x to the fourth. And that is our derivative. Okay. All right, and not really something you can memorize because you notice that the argument for the trig function is x squared, not just x. We could come up with something to memorize, but I don't see it as valuable, honestly. All right, so we have the same answer there. Let's go ahead and go on to the next problem and see if we can apply some of this to maybe a particle motion problem and see what we come up with. It says a particle moves along the x-axis so that its position at any time t is greater than or equal to 0 is written as x of t equals the arctangent of radical t. What is the velocity of the particle when t equals 9? So essentially I'm looking for v of 9. What is v of 9? What's the velocity when t equals 9? So how do we do this? Well, we have to figure out the velocity function first. So we have to take the derivative of this. But I know the derivative of position is velocity, but I don't know the derivative of arctangent. So I'm going to have to manipulate this to get my velocity function. Okay? So to do that, I'm going to take the tangent of both sides. So I end up with tangent of, let me rewrite this so you guys can see it. Let's just call this y equals arctangent of rad t, where x of t is equal to y. Y equals x of t is the position. That way we don't get so confused on x's and y's and variables and functions and all that. Take the tangent of both sides. We got tangent of y equals radical t. Taking the derivative of this, the derivative of tangent of y is secant squared y times y prime equals the derivative of rad t is going to be 1 over 2 rad t. And if you didn't see that, you would write rad t as t to the 1/2. Then that becomes 1/2 t to the negative 1/2, which simplifies to 1 over 2 rad t. And then isolating y prime, we have y prime equals 1 over 2 radical t times secant squared y. And then from here, we need to replace that y value. So we're going to do our triangle. Remember, we get our triangle from the basic trig function that we had a minute ago here. So, sorry, not that one, this one. Right, because we don't want any inverses in there. So tangent of y, that means y is my angle. Tangent, remember, is opposite over adjacent. So this would be rad t over 1, where that's my adjacent. We have to figure out our hypotenuse now. So we would say 1 squared plus rad t squared equals happy face squared. So we end up with 1 plus t equals happy face squared. And notice this cleans up pretty nicely because the rad t squared just becomes t. So t equals, then we square root both sides. So I guess it doesn't clean up too nicely. I thought I was solving for t for some reason. And so we end up with a happy face is equal to radical 1 plus t. And so on this side we have radical 1 plus t. Now what is secant? Remember secant of theta is equal to, there's a couple ways of writing it. You could say 1 over cosine, or you could think of the reciprocal of cosine. Since cosine is adjacent over hypotenuse, secant will be hypotenuse over adjacent. So in this case, we would get 1 over 2 radical t. Secant is hypotenuse over adjacent, so it's hypotenuse over adjacent. So it's times radical 1 plus t, and then we're squaring that result. and then simplifying it from there. So we get 1 over 2 rad t times, and then radical 1 plus t squared is just 1 plus t. We want to put that in parentheses. So here we have y prime. Now remember, what was y prime? Well, what was y? Y was x of t. Y was the position. So I'm going to go back and say, well, y prime is then x prime of t. That is my velocity, and x prime of t is my velocity function. Okay? So 2 rad t there, 1 plus t here, and that is my velocity function. Now I want v of 9. I'm just going to come over here and do that. V of 9 is going to be 1 over 2 radical 9 times 1 plus 9. And then simplifying that, we get 1 over 2 times radical 9 is 3 times 10. That's going to be 1 over 60. So v of 9 is 1 over 60. And I don't know if it gave us any units to work off of here. It did not. So we would just say that's my velocity when t equals 9, which means I'm heading in the right direction. I'm moving in the positive direction there. All right, let's double check our work to make sure that all makes sense. We've got tangent y equals rad t. Take the derivative, making sure we're using implicit differentiation and the chain rule. Then we're going to isolate y prime, and then we're going to write our triangle. Oh, I did it actually completely different here. Not completely different, but notice I got secant squared here on the bottom. That can turn into cosine squared on the top because that's a reciprocal. But regardless, I still need to know the y. Still need to replace that with something in terms of t. So if we're talking about tangent y equals rad t, we got the opposite and the adjacent. Doing the Pythagorean theorem, we get rad 1 plus t. And then plugging that in, cosine, according to this, cosine squared, well, cosine is going to be 1 over radical 1 plus t squared. So it's 1 over 1 plus t, which means it would go back down to the denominator there. But regardless, we end up with the same results. And then we go ahead and plug in 9 to our time and end up with exactly what we had before. Okay, so that's pretty straightforward. It's just it's a long process. It's a bit of work to do. All right, let's go ahead and take a look at one more practice problem that is dealing with inverse functions, I believe. And let's see if we can get this right, making sure we're using all our algebra properly. All right, it tells us y equals 1/3 arc sine of 2x, and we are looking for the normal line when x equals 0. All right, that's the question. Now, what do we need to do? Well, to find the normal line, we need two things. We need our point and we need our slope. Well, I don't like dealing with inverse functions at all, so I'm just going to get rid of this arc sine by taking the sine of both sides. But you have to be careful because we have this 1/3 out front. So what we have to do is actually get rid of that 1/3 first. So what I want to do, first step, is to multiply both sides by 3. And so we end up with 3y equals the arc sine of 2x. Then we can take the sine of both sides. So we end up with sine of 3y equals 2x. Oops. And then we can take the derivative of this. Well, the derivative of sine of something is cosine of that something times the derivative of that something. So what's the derivative of 3y? Well, that's 3y prime. And then the derivative of 2x is just 2. Solving for y prime, we have y prime equals 2 over 3 cosine of 3y. So that's not going to cut it because we need to get that in terms of x. That is where we do our triangle. So again, we're using this equation, that relationship, to figure out our triangle. What is our angle in this triangle if it says the sine of 3y? Well, the angle would be 3y. 2x would be our opposite, and 1 would be our hypotenuse because sine is opposite over hypotenuse. Then we would do the Pythagorean theorem on this. I'm not going to spend a whole long time on that. It's radical 1 minus 4x squared. And again, you can do the Pythagorean theorem to determine that yourself. And then substituting in here, we get y prime equals 2 over 3. What's cosine of 3y? Cosine of 3y is adjacent over hypotenuse, so it would just be radical 1 minus 4x squared. So that's my derivative. In order to find the normal line, I need to find the slope of the tangent line first. So we'd say y prime when x equals 0 is 2 over 3 radical 1 minus 4 times 0 squared. Simplifying that, that's a 0. 1 minus 0, 0. Radical 1 is, 1 minus 0 is 1. Radical 1 is 1. And so you end up with 2 over 3 as my derivative. So that's the slope of my tangent line. I need the slope of my normal line, which is the negative reciprocal or the opposite reciprocal. So I got my slope. The next thing I need is my point. Now, it's simple enough. We could just plug in 0 here and figure out what y is. But again, I don't like dealing with inverse functions, so I'm just going to use this equation right here. The sine of 3y is equal to 2 times 0. Okay? And so we end up with sine of 3y equals 0. So what is the value of y that produces 0 when I take the sine of 3y? So sine of what gives you 0? Sine of 0 gives you 0. And so that would imply that the inside there, let me do this. I'm going to replace 3y. I'm going to say let u equal 3y. Not that you have to do this. You can kind of think of it in your head a little bit. But if I say let u equal 3y, then this is actually saying sine of u equals 0. When does sine equal 0? It's when u equals 0. And since u equals 3y, I'm going to replace that back in. So we get 3y equals 0, so y equals 0. If y equals 0, 3 times 0 is 0. Sine of 0 is 0, so that makes sense. So the point that I have is actually 0, 0. And then from there, I'm going to create my normal line. So it would be y minus 0 equals negative 3 over 2 times x minus 0. That is the equation of the normal line. All right, let's double check to make sure that is all correct before we wrap it up here. We multiplied both sides by 3. We took the sine of both sides, took the derivative using the chain rule and implicit differentiation. We isolated y prime, and so we end up with 2 over 3 cosine of 3y. Doing our triangle here, the angle is 3y. Sine is opposite over hypotenuse, and then doing the Pythagorean Theorem, we get radical 1 minus 4x squared. Taking that, plugging that in for cosine of 3y, we get 2 over 3 times radical 1 minus 4x squared. Then we're going to plug in 0 for our x value to figure out the slope of our tangent line. Then we're going to flip and switch that to negative 3 over 2 for the slope of the normal line. And then we're going to figure out, I did something a little bit more in depth here. I got to figure out that point, and that point was, I guess, 0, 0, because when x is 0, y is going to be 0. So I showed the work here, but I didn't do it on the lesson there. That does simplify the same thing, though. All right, that wraps up the lesson dealing with the derivative of inverse trig functions. And you can see that it's all based on the idea of implicit differentiation, because the derivative of sine of 3y is cosine of 3y times 3y prime. Chain rule. And then we have y as a function, so the derivative is y prime there. And then the other big key important thing is to be able to develop the triangle in such a way that we can replace an expression that has y in it with an expression that has x in it. Okay, but other than that, everything just keeps plugging along the same way it always has, dealing with normal lines, dealing with particle motion, dealing with taking derivatives, and all of that. So if you have any questions, just like always, comment in the section below. And otherwise, I will talk to you all later.